Hi, welcome to this video lecture. Today I'm going to teach you about isotropic and anisotropic material behavior. So in engineering, you will often come across these two terms, isotropic and anisotropic. So let's try to understand what are the meanings of these two terms. And also, I would like to show you an experiment, a very easy experiment to show how we can differentiate between isotropic and anisotropic behavior of materials. So first of all, isotropic behavior. If we have a material, let's say we have a cube of this material. If this material has mechanical properties which are same in all directions, so let's say we have got Cartesian coordinates x, y, and z, and this is the material. If the properties, the mechanical properties such as modulus or strength of the material are same in all directions, in any direction you measure, you get the same property, then we call it isotropic. So mechanical properties are same in all directions, then it is called isotropic. Anisotropic is opposite of this. That means the mechanical properties in different directions are different. So if we measure the elastic modulus, for example, in this direction and in this direction, then they are different. Then we call this material as anisotropic. There are many materials which are isotropic, and also there are many materials which are anisotropic. So isotropic material could be, for example, a ceramic material or a casting. So for example, if you cast an object, so if you produce this by casting, then you might get mechanical properties which are all same in all directions. But in engineering, we produce things by many other kinds of manufacturing processes. For example, we produce wires by wire drawing. By drawing, we can produce a wire of material, or we also conduct rolling, for example. By rolling, we can reduce the cross-section or thickness of this material, and also we can make it very, very thin. So for example, sheet metals are produced by rolling. So among these, if we think about method such as casting or powder metallurgy, it will produce an object which is more or less isotropic. That means the properties are same in all directions. But if we produce things by drawing or by rolling, in this case the material will be anisotropic, because in this case we are deforming the material in certain direction, in one fixed direction. So therefore the material will have properties which are different in this direction, in the direction of drawing, compared to perpendicular to this one. So for example, by drawing we produce a sheet metal. by rolling we produce a sheet metal, and this is the direction of rolling. Then the properties in this direction will be different compared to properties in this direction. So this material will be anisotropic. So this kind of manufacturing processes will introduce anisotropic behavior in the material. So drawing, as well as, for example, making fiber by fiber spinning process. So from the melt we can spin the fiber. In this case also the fiber will have different properties in the longitudinal direction than in the transverse direction. There is another method which we use for manufacturing is making composites. So if we are making a composite and we have aligned the fibers in this direction, then obviously for this material the properties in this direction will be very different from properties in this direction. So this is called longitudinal direction, and this is called transverse direction. So properties in longitudinal direction will be different from the properties in transverse direction. In general, if the fibers are aligned in this longitudinal direction, then some of the properties are better in the case in the longitudinal direction, like a strength or modulus. In the transverse direction, the strength will be poorer. So this is also an isotropic material. So this is the whole concept of isotropic and anisotropic behavior of materials. Though the purpose of this video is to show you experimentally how isotropic and anisotropic materials behave, but here let me give you a very short theoretical background. So as I said, mechanical properties are same in all directions for isotropic material or isotropic behavior. So if we assume that this is an element, so this is the solid material, a very, very small element of this solid material, and we have direction x, y and z, and this element has dimensions of delta y, delta x and this side delta z. And these are all the stresses which has been identified here. So for example, sigma x is in this direction, so it is acting on this plane zy and acting in the direction of x. Similarly, sigma y is acting in this direction and sigma z is acting in this direction. Other stresses are all shear stresses. So for example, tau xz is acting on the plane normal to x-axis and acting in the direction of z-axis. So tau xz is acting on this plane. This plane is perpendicular to x direction. So first subscript x indicates the plane and the second subscript z indicates the direction. So it is acting on this plane but in this direction, in the direction of z. So tau xz. Similarly, all other shear stresses are also indicated here. So from the elastic theory, we know that stress-strain relationship for uniaxial stress will be given as this one. Strain is equal to sigma over E, where E is the Young's modulus. But if we have three-dimensional state of stress, that means we have stresses applied in all the directions x, y and z. In that case, the strain in x direction will be given by this equation. So this is the strain because of the sigma x working here, and this is because of sigma y and sigma z. Here sigma xx means on the plane normal to x and in the direction of x. Similarly, this on the plane normal to y in the direction of y, and similarly for sigma z. So here, using Poisson's relation, Poisson's relation is given by this one, transverse strain divided by the longitudinal strain. So here it gives us the strain because of the three stresses acting in the x direction, y direction and z direction. So basically, because of the stress in y direction and z direction, there will be a little bit of contraction. So similarly, we can write other equations as well. So this is well-known stress-strain relationship for isotropic material. That means the material properties, that is Young's modulus, is same in all directions. We have not differentiated. And we can also write the shear stress or shear strain by using shear modulus. So again, shear modulus is also same in all directions. And also we can interrelate shear modulus with the Young's modulus E by this relation using Poisson's ratio here. So these are all well-known relations. Another relation is bulk modulus K related to E. So basically we can relate G, E and K using Poisson's ratio here. So they are all interrelated. So these are well-known relations from theory of elasticity for isotropic material. Now if we are dealing with anisotropic behavior, that means the modulus, for example, is not same in all directions, then how do we deal with the material? So first of all, the mechanical properties are different in different directions. Again, we use the same element here. Each component of stress relates to all 6 components of strains, and also each component of strain relates to all 6 components of stresses. So here in this case, you see the extensional stress and the shear stress all contribute to strain. So for example, strain in 1 here, which 1 corresponds to x. So this is the conventional way of writing these equations. So epsilon 1 means basically epsilon xx will be given by this equation where S represents compliance. So S11, S12, S13, S14, these are all the compliance constants. And these are the stresses. Sigma 11 is basically sigma xx, sigma 22 is sigma yy, and so on. These are the shear stresses. So for this strain in the x direction, there is contribution from the extensional stresses as well as from the shear stresses. And this is the equation written. Similarly, we can write for epsilon 22, epsilon 33, all in the very similar fashion. And these are for the shear stresses, epsilon 23, epsilon 13, and epsilon 12. So we can complete this equation. So this will be the complete equation for anisotropic material. So that means these are the constants that we have to find out. These are the material constants here. So we don't have one single property like Young's modulus or shear modulus, but here we have got many values of these properties. So S, P, Q here are known as compliance constants or compliance tensor. Subscript PQ means row P and column Q. So if we make a tensor of compliance constants, then we can make a tensor of 6 columns and 6 rows. And P and Q indicates these columns and rows. So the above equation provides 6 by 6 matrix of compliant constants for an anisotropic material. And this tensor is given in this format. So these are all compliance constants. As you can see, just now we have seen in the equation. For plane stress conditions, so we will be talking about plane sheet of material. So in this case, many of the compliance constants will be cancelled out because we have only 1 and 2. So in that case, the stress and the extensional stress and the shear stress values are only in the XY plane, we assume. So therefore we will be left with these compliance constants for plane stress condition like a sheet of metal. And here we can find out the compliance constant as is equal to 1 over E1. So this is the Young's modulus in the direction X. Similarly, Young's modulus in direction Y, and this is the shear modulus on the plane 1, 2. Similarly, other relations can also be written down here. And these compliance constants are equated to 0. So this is a well-established analysis for anisotropic material. So my purpose of this video is to show you by experiments how we can see the difference between the properties. So we have conducted a test, and these tests we have conducted on facial tissue. So I will explain to you how facial tissue is very anisotropic material. So I will just explain to you the experiment, the tensile experiment that we have conducted. So specimen size was kept gauge length of 110 mm, width of 25 mm thickness, and width of 25 mm and thickness of 1 mm. And the cross head speed of this equipment was kept at 5 mm per minute. So we have conducted the test under these conditions. So first I will show you just by hand how we can see the difference in the mechanical property of facial tissue in different directions. So this is a sheet of one single sheet of facial tissue. So here you can see that although it's not very visible, but there is some impression that along this direction. And another thing you notice is it has been stacked like this. So basically the tissue is produced by the rolling process. So during rolling, paper pulp is passed through rollers, and as it passes it gets thinned down, and the water is slowly removed and the pulp slowly becomes a solid like this. So that's the process. So it is rolled. So just like sheet metal rolling, this is also rolled. So therefore I expect that this will have anisotropic behavior. So that means the property of this facial tissue will not be same in this direction and this direction. Now I have identified that the direction of rolling is this way because this has been stacked like this. Also sometimes you can see some impressions along this one, which indicates that they were kept under some pressure in the roll and it passed through like this. And another indication is that as it passes during the final stage, the tissue is folded like this in an automatic machine. So this folding is done by cutting first, and then it is folded this way. So this way many tissues will come. They, for example, so this tissue will be cut here, it will get folded in the machine, then this will get cut and this will get folded, and like this. So it automatically gets stacked. So therefore I can expect that the direction of rolling is this way. So my understanding is that because of this directional property, the fiber of this paper pulp has been all aligned in this direction because of rolling. So which means that this is the longitudinal direction of the fibers and this is the transverse direction of the fiber. So if we are going to pull, so here we will assess the strength of this tissue, facial tissue. If we are going to pull in this direction and we are going to pull in this direction, the properties will be different. So for example, if we pull in this direction another tissue. So this is the longitudinal direction. So in this case, I will pull in this direction. So I can feel that this tissue is very weak in the transverse direction and quite strong in the longitudinal direction. It takes a lot of stress. So later I will show you the test we have conducted on a tensile machine. Now another thing I should tell you about is because the fibers have been aligned in this direction, therefore if you tear the tissue along the fiber, then you get a nice cut, because the fibers are all aligned this direction, so we are not fracturing it across the fiber, but we are fracturing along the fiber, just like a bamboo. If you peel the bamboo along the fiber length, then it is quite easy. So the fibers are all aligned in this direction. This is the longitudinal direction. So it is very easy to peel. Now let me show you if I do a transverse direction peeling. So as I said, this is the longitudinal direction and this is the transverse direction. So now I will break it in the transverse direction and see what happens. It never goes in a very straight manner. It will always change its direction. That means the crack which you have created and you are pulling it, the crack always changes direction. And because of this direction change, this tissue is stronger when we pull in this direction or longitudinal direction, because when we are pulling it in longitudinal direction, what will happen? The crack from this direction will grow and it will make the fracture. But this crack can never go straight. It always gets diverted, and because of this it consumes a lot of energy and force, and therefore this is stronger in this direction. But in a transverse direction, if you see, so this is longitudinal direction, I turn it like this. In transverse direction it will be easier. Once the crack initiates, it goes through very easily because the fibers are aligned in this direction and I am pulling it in transverse direction. So through this experiment I have proven that a facial tissue which is made by a rolling process is very anisotropic. The fibers are aligned in this direction. Here we cannot see the fiber by naked eye, but these fibers are aligned in this direction. Therefore this tissue has very high strength in this direction and lower strength in this direction, which is the transverse direction. So that means if we measure strength or modulus, both will be different in different directions. So as you change the direction, the material property will change slowly from very high value to very low value. In between you get medium values. So this is the concept of anisotropic material, and I have shown you this example of anisotropic material. This exists in many engineering materials as well as natural materials like wood. Wood is also very anisotropic. So I will show you the results of tensile tests we have conducted. So tensile load displacement curve. So on the y-axis we have got the load, and on x-axis we have got millimeter. So this is an extension test. So here in the transverse direction, that means perpendicular to fiber alignment, we found that average maximum load at failure was 16.83 Newton. So this is the load displacement curve. So this is in Newton and this is in millimeter. So 3 tests we conducted and we got this kind of results. For the longitudinal direction, that means along the fiber alignment, we found that the load was very high and the average of the maximum load at failure was 46 Newton. This is quite high compared to the transverse load. So the conclusion we found is strength in longitudinal direction is 2.7 times higher than in the transverse direction. So in this very short demonstration, you have seen that a material, an engineering material, for example, a material which has been rolled like this, like a facial tissue paper, is very anisotropic in nature. Similarly, other materials like composite materials, it will be very anisotropic material. So you have learnt about isotropic behavior and anisotropic behavior of material. So thank you very much for joining this video lecture.